Hey class, here's another video for you all. This one's actually based on one of the workshop problems. So workshop problem 1 on workshop 7 is the one shown here. We have this race car. It's going to be going around, maybe it's like at some sort of a carnival or kind of a trick car show kind of place. So there's this conical shaped area, I guess, and the car is going to be zooming around in a horizontal circle. So it's going to be going around the cone in a circular path, as you can see here. And what you're asked to determine is if the car wants to be moving at a speed of 33.8 meters per second, and if it wants to be having zero reliance upon friction, meaning friction's not pointing up or down the slope. It could be either one, but in this case, it wants you to have no dependence on friction. If that were the case, then you're asked to determine what is this distance d shown here, okay? So that's what you're asked to figure out. When you first look at this problem, you might think, boy howdy, what is even going on? What am I supposed to do here? And that's always a good place to start with any physics problem because, yeah, you can only get better from there. So let's think about what's going on. So we know the car's moving in uniform circular motion. It has a constant speed, but its direction is constantly changing, and there's no reliance on friction. All right? So I'm going to go ahead. The first thing I think of is forces. Anytime we have uniform circular motion, it makes me think of centripetal force, which makes me think of some of the forces. So I went ahead and got
Would you say,
us.
may the force be with you?
May the force be with you is what my wife says as encouragement for us all to solve this problem. But yeah, so I got a free body diagram that I want to start with. So if I think about my car here, I know that I have the weight force going straight down. So in the downward direction, we got mass times gravity. And we know that there's going to be a normal force as a result of contact with the surface. So we have a normal force in this direction. Now, since our normal force is at an angle, we need to think about what angle that is. You could do some geometry to prove this, but since we know the slope is at an angle of 40 degrees, then what that means is this angle here is also going to be 40 degrees. All right, and you can prove that with geometry. If you need help with that, let me know. In addition to that, the only other force you could have would be friction, which could be either acting up the slope, or you could have a friction acting down the slope in the opposite direction, down this way. But in this problem, since we're asked to have no reliance on friction, we don't have either. All right, so let's just get rid of that. So we just have those two forces. Boy howdy, that looks pretty simple, huh? So if we are using the x and y axes I defined, we need to break our normal force into x and y components. So the normal force is going to have an x component, so its x component is going to be in this direction here, right? And so that's going to be the normal, and if we make a little triangle out of our normal force here, the x portion is the opposite side, so it's going to be normal multiplied by the sine of our angle 40, okay? And that's actually in the negative direction, so I'm going to go ahead and just insert a negative sign in here so I don't forget about that. And then my normal force in the y direction is going to be equal to the normal force times the cosine of that angle 40 degrees. Okay, so let's go ahead and start thinking about doing some of our forces. So we can do some of the forces in the x direction, and we can do some of the forces in the y direction. In the x direction, all right, we're going to have an acceleration in this direction. The centripetal acceleration towards the center of our circle, because of where the car is at, it's going to have a centripetal acceleration in that direction. So our net force is going to be equal to mass times centripetal acceleration, which is actually in the negative x direction. So I'm going to put a negative sign in there. In the y direction now, since we're staying in a uniform circle, we're not going to be accelerating up or down, so the acceleration in the y direction will be 0, and so the sum of the forces will be 0 in the y direction. So if you wanted to go ahead and try solving, again, we're not even sure where this d is going to come in, right? We're just trying things. Sometimes in physics, you got to jump in, see where it gets you, following the process that we know to be accurate. So in the x direction, what do we got? Well, all we have is the normal in the x direction. We have negative normal times the sine of 40 equals m times negative centripetal acceleration, which if you remember is v squared over r. Okay, so that's our x direction. In the y direction, what do we got? We have the normal in the y direction, force normal cosine 40, minus mg equals 0. Okay, that's easy enough. So our normal force is going to be equal to mg divided by cosine 40. That's cool, except that we don't know what m is, so that's a little bit tricky. Also, just kind of a side note, one thing I want you to notice, look here, our normal force in this case is going to be equal to mg divided by cosine of 40. So since cosine is always between 0, or really negative 1 and 1, cosine of 40 is going to be some number less than 1, so our normal force is actually larger than the weight of the vehicle. That's an interesting thing to note conceptually, because what that means is that the inertia of the car is pushing it into the ramp, making the normal force have to be larger than just the weight of the car. Pretty cool. So that's a fun little side note that we have there. But again, that doesn't tell us anything about D. Now let's look at our other equation over here. Over here we have negative normal sine mv squared over r. Still, we don't know m. We don't know the normal force.
Does negative normal
either.
weird?
So we could probably do some combination. You know, I can see we can substitute in normal force from this equation over. Let's go ahead, let's do that, and let's see where that gets us real quick. So the minus signs here on both sides, those will cancel out, so that's a bonus. And I'll substitute in normal force. So we found normal force to be mg over cosine 40, and we still have this sine 40. And so that's going to be equal to mv squared over r. Sine over cosine is tangent. Oh, look, our masses cancel. Boy, howdy, yes. All right, that's good. So I have g times the tangent of the angle theta equals v squared over r. All right, so this is looking nice. But again, we're asked to find this distance d again, okay? Wait a second. I don't have d anywhere in my equation. What is going on? Well, what do I have? I know v, that's given to me. I know theta, that's given to me, and I know what g is. So the one thing in this equation I don't know is r. Where is r? I haven't even labeled it on my picture. Oh man, let's go over here. This right here, this distance right here is r. So if you look, I'm going to take this and redraw it down here, because what we have is we have this side here, which is r, some vertical distance, which we don't know, and this diagonal here, which is d. And we're told that this right here is a 40-degree angle, which means this is 50 degrees, and this angle is 40 degrees here. So what we can see from this right triangle is you could look at this and be like, hey, D is my hypotenuse. If I use the angle 40, then cosine would relate R, which is what we're trying to, or what we have in our equation, to D. I'm going to rewrite this R as a lowercase r since that's what's in my equation. But these two R's here are the same thing. So what we can observe is that R is just equal to D times the cosine of the angle 40. So we can call it theta, or we can just label it as 40. So D is going to be equal to R over cosine of 40. So you can either substitute in right here, or you can just solve for R, divide by cosine 40, and that will give you D. So going back to the original problem, if we want to solve for R, we can multiply both sides by R, so you get R times D tangent of theta, which at some point I changed 40 to theta, so let's just pop that back to 40. And that's equal to V squared. Then dividing by G tan theta, to get rid of that, you get R equals V squared over G tan 40. So from that you can solve for R, plug it in, solve for D, and you get a box-worthy solution. So I hope that helps you guys out a little bit. This is a tricky question, but a lot of good concepts are covered with it, so hopefully that makes sense. If you still have questions, please let me know.